Hello, and welcome to a module on aerosol properties. In everyday use, the term aerosol refers to a product like a paint, a perfume, or a lubricant, or maybe even a medicine, delivered as a spray or mist from a container filled with a liquid and a gas phase propellant, as shown in the diagram and image. In scientific fields, however, the word aerosol has a broader definition. Scientifically, we define an aerosol as a suspension of liquid or solid particles in a gas. While we may mostly think about the particles when we talk about aerosols, it's important to note that the aerosol is not just the particles. It also includes the gas phase in which the particles are suspended. There are many sources of aerosols, both naturally occurring and man-made. This figure from Andrei and co-authors illustrates some of the sources of naturally occurring aerosols. Volcanoes and wildfires over on the right-hand side contribute aerosol particles to the atmosphere directly. Wind-blown dust from desert sands and other dry surfaces also become aerosol particles, as shown in the center of the illustration. Many plants release pollen, and many fungi and bacteria release spores. These can all be classified as biological particles. In addition to releasing particles directly to the atmosphere, plants can release volatile organic compounds, or VOCs, which undergo chemical reactions in the atmosphere to form what are called secondary organic aerosols. Winds and breaking surf can release droplets from the surfaces of oceans and other bodies of water, contributing salt particles, organic matter, and biological particles to the atmosphere. Volcanoes emit sulfur dioxide to the atmosphere, while plankton and other organisms release dimethyl sulfide from the oceans. Both of these compounds can undergo chemical reactions in the atmosphere to form sulfate particles. As just mentioned, volcanoes like Mount St. Helens in Washington State in 1980 are a natural source of aerosols. Powerful volcanoes can produce aerosol particles that can linger in the atmosphere. These particles may reduce the amount of light reaching the ground so that global temperatures are slightly reduced for as long as a year or more. Wildfires produce smoke particles that can make the atmosphere dangerous to breathe near the fires. The particles can also be transported long distances across regions and national borders, worsening air quality for communities along the way. Rainbows are observed due to the interaction of sunlight with water droplets suspended in the air. Often, hills farther away appear to be lighter than closer hills due to the scattering of light by aerosol particles, as in this image from the Great Smoky Mountains of North Carolina and Tennessee. The reds, oranges, and yellows of beautiful sunsets are produced by the preferential scatter of blue and green wavelengths of sunlight by aerosol droplets and particles in the atmosphere. Aerosols are also created by human activities. Here are a few examples. Cutting of a concrete block with a power tool generates an aerosol composed of solid particles, often referred to as dust. The application of pesticides from an airplane as aerosol drops is an example of a spray. Cooking produces smoke, complicated aerosol particles comprised of solid products from a combustion process, along with volatile and semi-volatile compounds condensing from the surrounding air. Hot processes such as welding produce vapors that almost immediately condense into liquid or solid aerosol particles referred to as fumes. Rotating processes can produce mist droplets if they are wet. An example is when metalworking fluids are used to cool, lubricate, and clean metal parts and tools during machining. Aerosol generation processes can usually be thought of as being either top-down or bottom-up processes. Top-down processes involve mechanical generation in which energy is supplied to a bulk solid or liquid material, breaking it up into smaller aerosolized particles. Examples from the previous images include cutting and spraying. The particle size depends on the amount of energy supplied by the process relative to the energy of the bonds adhering the material together. Generally, smaller particles are generated when more energy is applied. Bottom-up processes involve nucleation, in which vapors, often from hot processes, condense onto tiny groupings of molecules called nuclei, followed by further growth of the nuclei into particles by way of additional condensation. These particles often join together in a process called coagulation, leading to effectively larger particles. Cooking and welding are examples of processes producing bottom-up aerosol particles. This short video shows an example of mechanical generation of aerosols by the cutting of concrete. The dust being emitted by the cutting process is easily visible. This video shows an example of nucleation and growth from a welding process that is producing fumes. These particles are also visible, primarily due to the scattering of the strong light generated by the welding arc. We know that 1 micrometer is 1 times 10 to the minus 6th meter, and that 1 nanometer is 1 times 10 to the minus 9th meter. Aerosol particles range from about 1 nanometer to 100 micrometers, about 5 orders of magnitude, or factors of 10. Objects smaller than 1 nanometer are on the molecular scale. They are no longer particles, while objects larger than about 100 micrometers settle due to gravity very quickly. To put these differences in perspective in another way, let's imagine that the Empire State Building, which is 1,454 feet tall to its tip, is only 100 micrometers tall. Objects roughly 100 micrometers in size are about the largest objects that can remain airborne long enough to be inhaled into a person's respiratory system. If the Empire State Building is 100 micrometers tall, the Great Pyramid at Giza would be 31 micrometers tall. A tennis court like Center Court at Wimbledon would be 5.4 micrometers long. An adult male giraffe would be roughly 1.2 micrometers tall. If the Empire State Building were 100 micrometers tall, LeBron James would be 0.46 micrometer or 460 nanometers tall. R2-D2 would be 250 nanometers tall. An official FIFA soccer ball would have a diameter of 50 nanometers. A can of Diet Mountain Dew would be 15 nanometers in diameter at its widest. Finally, an M&M would be 2.3 nanometers in diameter if the Empire State Building were 100 micrometers tall. You can imagine that if someone were to throw a normal-sized M&M at you, it might sting. If it were thrown at you hard enough, it could injure your eye. If your mouth were open when the M&M was thrown, it could get stuck in your windpipe. A child could stick an M&M up its nose. You could eat too many M&Ms at a sitting and make yourself sick, or too many over your lifetime and make yourself fat. These are all potential health effects from exposures to M&Ms. If someone were to throw the real Empire State Building at you, it would do more than sting. You would certainly injure yourself if you tried to eat the Empire State Building or stick it up your nose. The health effects of exposure to an M&M and the Empire State Building differ mostly due to their orders of magnitude size difference. Likewise, you can imagine the objects that are on the micrometer scale and the nanometer scale may cause different health effects in humans because of their size differences. Therefore, it's important to be able to predict and describe the behavior of aerosol particles as a function of size. We commonly refer to particles larger than 1 micrometer or 1,000 nanometers as coarse particles. We call particles smaller than 1 micrometer fine particles. Particles smaller than 100 nanometers are called ultrafine particles or nanoparticles, although this last term is usually reserved for particles intentionally created for a purpose. For additional perspective on these small sizes, it is useful to remember that human hair is about 50 to 70 micrometers in diameter, and that the wavelengths of visible light range from about 0.4 to 0.7 micrometers, or about 400 to 700 nanometers. These curves show the typical prevalence of particles in the outdoor atmosphere on the vertical axes as a function of particle size on the horizontal axis, using the number of particles, their surface area, and their mass as metrics. The metric matters because larger particles have more surface area and mass than smaller ones. We can also see there are different modes of particles, indicating that particles form in different ways. The mode larger than 1 micrometer is called the coarse mode, while the modes comprising the fine, ultrafine, and nanoparticles smaller than 1 micrometer are called the nucleation and accumulation modes. As already mentioned, particles are generated in two primary ways, from the top down and from the bottom up. In top-down generation, particles are created from larger bulk materials forming the coarse mode particles. Workplace examples include aerosol particles from metal grinding, sawdust, and metalworking fluid mist from machining processes. This mechanical generation leads to coarse mode particles that are frequently referred to as dusts, mists, or sprays. In bottom-up generation, aerosol particles are formed from vapors. Small numbers of vapor molecules come together to form the smallest particle mode, the nucleation mode. Then they grow by processes such as additional vapor condensation and coagulation of particles to form a larger accumulation mode. Examples include welding fumes, combustion particles, 3D printing fumes, and many types of engineered nanoparticles. This particle formation from vapor molecules creates particles referred to as fumes, smokes, or smog. In addition to a broad range of sizes, aerosol particles come in a wide variety of shapes, including solid spherical particles like these amorphous silica particles, and spherical liquid particles like these water droplets, crystalline particles like these calcite particles, a form of calcium carbonate, pollen particles that have a wide range of exotic shapes, and fibrous particles of many different kinds, including fabrics, refractory ceramic fibers, asbestos, and carbon nanotubes. Particles that bump into each other can stick together to form chain agglomerates, like these silicon dioxide particles. We can classify particles by shape into several categories. The spherical, crystalline, and even the pollen particles are considered isometric because their sizes in all three dimensions are about the same. Platelets are like tiny sheets of paper. They have one dimension that is much smaller than the other two. An example of a platelet is a clay particle. Fibers have two dimensions that are much smaller than the third. We saw an image of an agglomerate, a chain of smaller primary particles, on the previous slide. When the agglomerate becomes long, they may collapse upon themselves and become more tightly bound. When they do this, they are referred to as aggregates, effectively forming a new particle. Another important property of particles is their density, which varies depending on composition. Pollen particles have a density between 0.4 and 1 gram per cubic centimeter. Oil particles have a density of about 0.9 gram per cubic centimeter. Water droplets have a density of 1 gram per cubic centimeter. Sand or silica particles have a density of about 2.5 grams per cubic centimeter, while elemental lead particles have a density of 11.3 grams per cubic centimeter. The densities of all of these particles are about 1,000 times higher, or even 10,000 times higher in the case of lead, than the density of air. Once an aerosol is created, the size and composition of its particles can evolve over time. This is especially true for fine and ultrafine particles. Once vapor molecules form tiny particle nuclei, they can combine to form larger particles through coagulation. Particles diffuse through the air and bump into each other, sticking together to form larger particles. Condensation and evaporation processes can further alter the size and composition of the particles. These phenomena play an important role in the exposure to aerosols that human beings face. Depending on where people are located with respect to these processes, they would be exposed to different aerosol particle sizes, compositions, and concentrations. Size, shape, and density will all affect aerosol particle behavior. We might now ask, what dimension is the most useful to define the size of a particle? Spheres of the same size but different composition and density, for example, an air bubble and a lead particle, will behave very differently. Is their physical diameter the most relevant way to characterize them? Alternatively, particles that have different sizes, shapes, and densities may behave similarly in certain conditions. Wouldn't it be helpful to have a parameter that reflects this similarity in behavior? Therefore, we might seek a way to describe particle size using behaviors influenced by particle properties. A concept that uses this approach is referred to as equivalent diameters. Equivalent diameters are important in characterizing and measuring particles. To use this concept, consider a real particle, which can have any size, shape, and density, together with an imaginary sphere. The next step is to keep some property the same between the real particle and the imaginary sphere. This property could be volume, surface area, gravitational settling time, electrical charge, light scattering, or something else. We then characterize the real particle in terms of the diameter of the imaginary sphere that has the same quantity of the property we've selected. Thus, equivalent diameter is the diameter of the imaginary sphere that has the same value of a selected physical property as the real particle. Let's consider some examples. In this slide, we have a real particle that is irregularly shaped and is made of a material with a density rho sub p. How can we describe the size of this irregularly shaped particle in terms of imaginary spherical particles? We can consider several different physical properties as the basis for an equivalent diameter. For example, we can imagine a sphere with the same projected surface area as our actual particle. We think of the projected surface area as the area of a shadow cast by the particle on a projection screen, and the diameter of the imaginary sphere would be the projected surface area equivalent diameter. This would be useful for characterizing particles under a microscope. Alternatively, you can imagine a sphere with the same total surface area as the surface area of the real particle. This sphere's diameter would be the surface area equivalent diameter. We can also imagine a sphere with the same volume as the real particle. The diameter of this sphere would be the volume equivalent diameter. As a final example, we can imagine a spherical water droplet with the same speed of falling through air due to gravity, also known as its terminal settling velocity, as the real particle. The diameter of this water droplet is called the aerodynamic equivalent diameter, or simply the aerodynamic diameter. Next, let's talk about particle size distributions and how they can be quantified and visually represented. A monodisperse aerosol is one in which all the particles are of the same size. They are almost never found in nature and are rare in workplaces. They can only be generated with difficulty in highly controlled situations. Most aerosols are polydisperse, composed of particles having a range of sizes. Almost all natural and workplace aerosols are polydisperse. Particle size distributions can be characterized using statistics that describe central tendency and variability. The median diameter of a distribution is the size that 50% of the particles have a diameter equal to or smaller than, and also that 50% have a diameter equal to or larger than. It is the 50th percentile of the diameters of all of the particles in the distribution. When the sizes of particles in a distribution are measured, they are almost always classified into a pre-established number of size intervals. Each interval I has a characteristic diameter d sub I. The number of particles measured in each interval is n sub I. The arithmetic mean diameter, d bar, is then the sum of ni times di across all size intervals, n, divided by the total number of particles in the sample, which is the sum of all n sub I. Variability can be assessed using a standard deviation, which is the square root of the sum across all size intervals of n sub I times the difference between d sub I and the mean diameter squared, divided by the total number of particles minus 1. Let's apply these statistics to a particle size distribution represented in this table. We will use this distribution across the rest of this presentation. Particles are divided into 8 size intervals in the first column with some sort of equivalent diameter, let's say an aerodynamic diameter, ranging from 0.003 micrometer to 0.01 micrometer, or from 3 to 10 nanometers, up to 10 to 30 micrometers. In the second column, the midpoint of each size interval is calculated as the representative size for that interval by averaging the lower and upper sizes of the interval. For our calculations, we will make a simplifying assumption that all particles within each size interval are the same size, this midpoint diameter. The numbers of particles present in each size interval are provided in the third column. The total number of particles is 19,952. To calculate the medium size, recall that 50% of the particles are equal to or smaller than the median diameter. 1/2 of 19,952 particles is 9,976 particles. Thus, 9,976 particles are smaller than or equal in diameter to the median diameter. The sum of the particles in the smallest two intervals is 7,489, less than 9,976. The sum in the smallest three intervals is 16,780, greater than 9,976. Thus, the median is in the third size interval, 0.03 to 0.1 micrometer. As the representative diameter for the third interval is 0.065 micrometer, that is the median diameter. To calculate the mean diameter, I added a fourth column to the table in which I have multiplied the number of particles, n sub I, by the midpoint diameter, which is the representative diameter we will use for d sub I. The sum at the bottom of the fourth column is 1,501.6 micrometers. Dividing that value by the total number of particles, 19,952, yields an arithmetic mean diameter of 0.0753 micrometer. This is similar to the median diameter, but slightly larger. To calculate the standard deviation, I have added yet another column in which I multiply the number of particles in the interval by the square of the difference between the midpoint diameter and the mean diameter of 0.0753 micrometer. To calculate the standard deviation, I have added yet another column in which I multiply the number of particles in the interval by the square of the difference between the midpoint diameter and the mean diameter of 0.0753 micrometer. The sum at the bottom of that column is 176.31 square micrometers. Plugging that value into the formula yields a standard deviation of 0.0940 micrometer. It may be of interest to note that the standard deviation is larger than the arithmetic mean. Let's make some graphs to visualize the data in the table. First, let's plot a simple histogram which shows a bar for each size interval. The width of the bar on the horizontal axis covers the diameter interval, and the height of the bar is the particle count. Because the diameter range is so wide, from 0.003 micrometer to 30 micrometers, and the diameter intervals become increasingly larger going down the table, it is difficult to see most of the data on the histogram. If we only plot the non-zero data 3 micrometers and smaller, the histogram is a little more readable. The particles are not normally distributed. If they were, the histogram would have a bell-like shape rather than being skewed to the right, and the standard deviation would be smaller than the arithmetic mean. This brings up the possibility of using alternative ways to visualize the data. One way is to consider that the particle diameters may be represented by a log-normal distribution. On a linear axis, aerosol size distributions are usually positively skewed with a tail to the right, as with the data we have already visualized. Distributions of the logarithms of particle sizes are usually more symmetrical, and the logarithms of particle size may then be represented by a normal distribution. If this is the case, the particle sizes are said to be log-normally distributed. This is often a good way to characterize particle size distributions. If we take the same size distribution and create a histogram on a logarithmic horizontal axis for diameter instead of a linear one, the data are much easier to visualize and the distribution is symmetrical, taking on the appearance of a bell shape. The particle diameters are much closer to being log-normally distributed than to being normally distributed. Note that we have selected a new representative diameter in the second column. Rather than the midpoint diameter, I've calculated the geometric midpoint diameter. This is taken by averaging the logarithms of the lower and upper diameters of the interval, and then unlogging the average. The geometric midpoint diameter can also be calculated by multiplying the lower diameter of the interval times the upper diameter, and then taking the square root of this product. If you have a log-normal distribution, it no longer makes sense to characterize the distribution using a mean and a standard deviation. After all, for this distribution, the standard deviation is greater than the mean, which does not make much sense. We characterize a log-normal distribution using a geometric mean and a geometric standard deviation. The geometric mean diameter, d sub g, is calculated similarly to the mean diameter, except that the mean diameter is replaced by the logarithm of d sub g, and the individual diameters in each size interval are replaced with the logarithm of the representative diameter. In this case, the geometric midpoint diameter. I generally use base 10 logarithms in these calculations, although they will also work with natural logarithms. The logarithm of the geometric standard deviation, sigma sub g, is calculated similarly to a standard deviation. The square root of the sum across all size intervals of the number of particles in each interval times the difference between the logarithm of the geometric midpoint diameter for the interval and the logarithm of the geometric mean diameter squared divided by the total number of particles minus 1. The term in the numerator can also be calculated by dividing each geometric midpoint diameter by the geometric mean diameter and then taking the logarithm before taking the square of the value and multiplying by the number of particles in the interval. It's important to note that the geometric standard deviation is a dimensionless number. As shown in the circled equation, all units will cancel during the calculation. Let's apply these formulas to our size distribution. In addition to the particle size interval, the geometric midpoint diameter, and the particle count columns, I have added a fourth column with the logarithm of the geometric midpoint diameter, log d sub I, and a fifth column with the third and fourth columns multiplied to give n sub I times log d sub I. The sum at the bottom of the fifth column is minus 27,814, which when divided by the total of 19,952 particles yields a value of minus 1.3940 for the logarithm of d sub g. Taking 10 to the power minus 1.3940 will give the geometric mean as 0.0404 micrometer, which is a little smaller than the median and arithmetic mean diameters for the particle size distribution. To calculate the geometric standard deviation, I have replaced the fifth column with the calculation in which I multiply the number of particles in the interval by the square of the difference between the logarithm of the geometric midpoint diameter and the logarithm of the geometric mean diameter. The sum at the bottom of that column is 3,470. Dividing that value by 19,952 minus 1, and then taking the square root, leaves us with a value of 0.4170 for the logarithm of sigma g. Taking 10 to the power 0.4170 will give the geometric standard deviation as 2.61. This is a dimensionless value. Confidence intervals around the geometric mean are calculated by multiplying and dividing the geometric mean by factors of the geometric standard deviation, rather than by adding and subtracting. Another important consideration in presenting histograms of particle size distributions is the interval width. Here we have our table of particle counts and a histogram plotted on a logarithmic scale for diameter. Suppose, however, that the way we measured the diameters of the particles left us with only 4 intervals rather than 8. This new table leaves us with the same total number of particles, but most of the size intervals have more particles because the intervals are wider. If we plot the data in this new table on the same histogram as the old table, the histogram looks taller, and the total area under the histogram bars is greater. It makes it look like the new table has more total particles when the number is the same. The way around this issue is to normalize the size distribution data by the widths of the size intervals. Let's look at the original data. In the second column, I have replaced the geometric midpoint diameter with the interval size on a logarithmic basis by subtracting the logarithm of the lower diameter of each interval from the logarithm of the upper diameter. In the fourth column, I then take the particle count from the third column and divide it by the interval size from the second column to give a normalized particle count, n sub I, divided by the change in logarithm of diameter across the interval, delta log di. When this normalized count is plotted against the logarithm of diameter, the histogram looks similar to the previous histogram, though with a different vertical scale. If the interval widths were less uniform than they are, the histogram would look less similar. I can perform the same calculations on the table with the reduced number of size intervals. When we plot the normalized counts with fewer intervals on the same histogram as the original data, the bars are more similarly sized and the areas under the curve are similar. Thus, normalizing particle size data by the widths of the measurement intervals is the preferred way to present size distribution data, especially if you hope to compare measurements made using different interval widths. Histograms are frequently awkward to work with. Curves are often easier. With the normalized counts from our original size distribution, we have plotted this histogram using a logarithmic scale for diameter on the horizontal axis. In addition to this, suppose we now plot the normalized counts against the geometric midpoint diameter for each interval. This curve is also a good way to represent the data, and it is easier to draw. The points are connected by straight lines, which is usually the most accurate way to represent the data. Particle size distribution data are most often plotted as curves. So far, we have looked exclusively at numbers of particles. Often we measure the number of particles in a certain volume of air, which we refer to as the number concentration. A common unit for this is number of particles per cubic centimeter of air. In a size interval I, the number concentration can be designated as C sub Ni. There are additional concentration metrics, however. Surface area concentrations can be measured in units of micrometers squared per cubic centimeter. For spherical particles, the formula for surface area concentration is the number concentration times pi times the square of the representative particle diameter for the size interval. Volume concentrations, though not commonly used, can be calculated for spherical particles as the number concentration times pi over 6 times the particle diameter to the third power. Mass concentrations with units of milligrams per cubic meter or possibly micrograms per cubic meter can be calculated for spherical particles as the number concentration times the particle density times pi over 6 times the particle diameter to the third power. As particles increase in diameter, they have much more surface area and much more mass. This table shows our particle size intervals, geometric midpoint diameters for each interval, our particle numbers turned into number concentrations with units of number per cubic centimeter, the width of the size interval on a logarithmic scale, and our particle number concentration normalized by the interval width. This curve is our particle number concentration normalized by the interval width from the table we just looked at, plotted against the geometric midpoint diameter. This is referred to as our size distribution by number. Note that the peak is at 0.0548 micrometers. This table shows the size intervals, geometric midpoint diameters, and number concentrations in the first three columns. In the fourth column is the surface area of an individual spherical particle having the geometric midpoint diameter. The fifth column is the surface area concentration for all particles in the size interval, calculated by multiplying the number concentration by the surface area for an individual particle. The interval size in the sixth column is divided into the surface area concentration from the fifth column to yield a normalized surface area concentration in the final column in units of micrometers squared per cubic centimeter. The curve on this slide is the normalized particle surface area concentration that we just determined, plotted against the geometric midpoint diameter. This is referred to as our size distribution by surface area. Note that the peak is at 0.173 micrometer versus the size distribution by number that had a peak at a smaller diameter. The change peak happens because larger particles have greater surface area than smaller ones. Similar to the table for surface area, this one shows calculations for mass. In the fourth column is the mass of an individual spherical particle having the geometric midpoint diameter in the interval, assuming a particle density of 1 gram per cubic centimeter. The fifth column is the mass concentration for all particles in the size interval, and the interval sizes in the sixth column are divided into the mass concentrations to provide normalized mass concentrations in the final column in units of milligrams per cubic meter. The curve on this slide is the particle mass concentration normalized by the interval width, plotted against the geometric midpoint diameter. This is referred to as our size distribution by mass. The peak is at 0.548 micrometer for the size distribution by mass. This peak occurs at an even larger particle size than in the size distributions by number and surface area because larger particles carry much more mass than smaller particles. Size distributions by number, surface area, and mass are excellent visual representations of the central tendencies and variabilities of the distributions, especially when they are plotted on a logarithmic diameter scale. However, it can be difficult to compare the shapes of distributions if the concentrations are exceedingly different or if you have to consider different metrics simultaneously. An alternative is particle frequency distributions. This table shows our particle size intervals, geometric midpoint diameters, and particle number concentrations in the first three columns. The total number concentration of particles is summed at the bottom of the third column. The fourth column is the fraction of particles in each size interval, taken by dividing the number concentration in each interval by the sum in the bottom row. The interval sizes in the fifth column are divided into the fractions in the fourth column to give normalized frequencies by number in the sixth column. This figure shows the particle frequency by number from the table on the last slide, plotted against the geometric midpoint diameter. This is the frequency distribution by number. The shape is the same as for the size distribution by number. Integrating the area under this curve would give us a value of 1. In this table, we calculate the frequency distribution by surface area. Columns 1 through 5 show the particle size intervals, geometric midpoint diameters, particle number concentrations, surface areas for individual spherical particles, and the particle surface area concentrations for each interval. The total surface area concentration, including all size intervals, is 662.2 micrometers squared per cubic centimeter, as shown by the sum in the bottom row of the fifth column. In column 6, the surface area concentration in each interval is divided by the total surface area concentration to yield the fraction of the surface area in each interval. After dividing by the interval widths in column 7, the normalized frequencies by surface area are shown in the final column. This figure shows both the particle frequency distribution by number along with the particle frequency distribution by surface area. This shows how you can compare the distributions by different metrics on the same figure. Note the shift in the distribution by surface area to larger particle sizes. In this table, we calculate the frequency distribution by mass in a similar way as we did for surface area. Columns 1 through 5 show the particle size intervals, geometric midpoint diameters, particle number concentrations, masses for individual spherical particles, and the particle mass concentrations for each interval. The total mass concentration, including all size intervals, is 0.0431 milligram per cubic meter, as shown in the bottom row of column 5. In column 6, the mass concentrations are divided by the total mass concentration to yield the fraction of the mass in each interval. After dividing by the interval widths in column 7, the normalized frequencies by mass are shown in column 8. This figure shows the particle frequency distributions by number, surface area, and mass all together. The distributions shift to larger particle sizes as you go from number to surface area to mass because the number frequencies are provided independent of particle diameter. The surface area frequencies depend on particle diameter to the second power, and the mass frequencies depend on particle diameter to the third power. This dependence on particle size of distributions created using different concentration metrics is illustrated through this figure along with the next two. This shows two size distributions by number. The blue curve is our original size distribution, which was created assuming a geometric mean of 0.04 micrometer, a geometric standard deviation of 2.5, and a total particle concentration of 20,000 particles per cubic centimeter. The numbers we calculated for this data were slightly different from these because the size intervals in our tables did not encompass all particles in the distribution. The magenta curve shows a size distribution created assuming a larger geometric mean of 0.4 micrometer, the same geometric standard deviation of 2.5, and a lower total particle concentration of 2,000 particles per cubic centimeter. The peak of the new distribution is far to the right of the original distribution, but it is much lower. This figure shows size distributions by surface area for the same two sets of particles. Note that the surface area concentration of the new distribution is greater than the surface area concentration of the original distribution, even though the original distribution has 10 times as many particles. In fact, the new distribution has about 10 times the surface area because it is comprised of particles that are 10 times as large. Because the surface area depends on diameter to the second power, the increase in particle diameter by a factor of 10 more than makes up for having 1/10 as many particles. This figure shows size distributions by mass for the two sets of particles. The mass concentration of the new distribution is 100 times larger than the mass concentration of the original distribution. Because mass depends on diameter to the third power, the increase in particle diameter by a factor of 10 far outweighs having 1/10 as many particles. These figures demonstrate that the measurement metric you use is vitally important when considering how to characterize particles. Often, it may be important to measure particles using multiple metrics. These figures from a 1992 research paper by Cantrell and Rubo show how size distributions by mass can be used to identify and characterize different types of workplace aerosol pollutants. The figure on the left shows the size distribution by mass measured in an underground coal mine that used vehicles and equipment powered by diesel fuel. The distribution shows two modes: a larger mode that incorporates top-down coal dust particles produced by the mining process, and a smaller mode comprised of bottom-up particles resulting from diesel combustion. Where this is size distribution by number instead of mass, the fine diesel particle mode would be much larger than the coarse coal dust particle mode. On the figure to the right is the size distribution by mass in an underground coal mine that used no diesel vehicles or equipment. The smaller mode is mostly absent, with only the coarse coal dust mode being evident. This shows the potential effectiveness of a switch from diesel to electric equipment at reducing fine particle exposures.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.